Assalamualaikum and good day. My name is Diana Natasha binti Abdullah Safri, and I will be presenting on our lab practical 1. The objective for this lab practical is to demonstrate a secure file transfer by applying AES encryption and decryption processes on an image file. For this demonstration purposes, I will be using an image file. So in this task, we developed a Java command line tool that encrypts and decrypts files using AES in Galois counter mode, GCM, where we provide an input file, output file, a password, and a key size to perform secure encryption and decryption processes. So the workflow is from encryption, then transfer, then decrypt. So in the system or in the folder, I've made a sender and receiver file inside in a single file titled secure transfer lab, where the whole transferring from sender to receiver will be safe and secured. So in the sender file, there's two files. One is an image file and one is a text file. But for this demonstration, I will be using the image file only. So for encryption process, we will have to go to we have to right click the main project, which is secure transfer AES. Right click, go to properties, and then go to runs, and then in the argument we have to write this we have to type in encrypt the input file, which is the full address of your image file, and then the output file, which is another file that will be created after encryption, but instead of the image file name, for example, in the input file we put image.jpg. So for the output we change to image 192. For this demonstration purposes, I will be putting 192. We set a password, so I put my password, and then for the key size, it's 192. Then after that, click OK. Then the output of this file being encryption would be here. Encryption completed is the path to the sender, or the path to the image file, encrypted file. Then after encryption process, you should see the bin file inside the sender folder. Move it to the receiver folder, the bin file, and then to decrypt that encrypted file from receiver, go back to the argument of the secure file transfer AES project. Right click on the project, go to properties, run, and then replace the input file as image.jpg. You replace it with the output file you made from encryption, so it's image192.bin. And then the output file, or the output the output file would I put as image_decrypted.jpg. So keeping the original file format for image is necessary to revert back or to decrypt the image instead of it being a text file, or it has to be a file format for us to access and see the content of that file. Then put the same password as you use for encryption. So this one I use my password and then put in the same key size. So I put 192. Then click OK. After click OK, then you should see the decryption or the output. The output should be encryption, decryption completed. And then that's the file to the decrypted image. Then to verify that both sender and receiver are getting the same hash value, or to verify that their files are not being tampered or modified during the transfer of encrypted file, we have to go to we have to verify it using Windows PowerShell. So open a terminal, open the PowerShell terminal, and type in cd. Change the directory of the terminal to the sender folder. So here I changed. I put cd documents / netbean projects secure file transfer AES secure transfer lab and sender. So it leads all to the sender folder for the terminal to run the process of getting the hash file. Then we write the command get file hash image.jpg algorithm SHA-256. We have to write it in SHA-256 and not SHA-192 because in the algorithm or in the PowerShell algorithm, SHA only uses SHA-1, SHA-256, SHA-512, if I'm not mistaken. Yep. It doesn't have SHA-192 in the family. So we can either use SHA-1 or SHA-256. But for this demonstration, SHA-256 is used. So here you can see the algorithm SHA-256 and the hash is 2C3E CDD C7D2A all the way to A08CD. That's the hash file for the sender's image JPG, or the original file before encryption. Then we can go to verify whether the transfer file of the encrypted file transfer is unaltered. Open up a new terminal. Do the same thing, but instead of leading it to the sender folder, we lead to the receiver folder. So cd documents, netbean projects, secure file transfer AES, secure transfer lab, and receiver. So the terminal will be in the directory of the receiver folder. Then put the same command, get file hash, but instead of image.jpg, we are using the decrypted JPG file. So get file hash image underscore decrypted dot JPG, and then use the same algorithm as we used for the previous step, SHA-256. So here we can see the algorithm is SHA-256 and the hash value is 2C3E C7D2A all the way to A08CD. So the hash values for before encryption and after decryption are both the same for the same file. That means the file is not modified, altered, or have tampered with during the transfer from sender to receiver. So here, me and my friends have made other few more examples on encryption and decryption processes on a different file formats with the text file and a PNG file, and we use all three all three key sizes 128, 192, and 256, and both encryption and decryption processes are a success and verified using the SHA-256 hash uh, algorithm, and both encryption and decryption hash values are the same. Next, we will be looking at the strength, limitation, and improvements that can be made for this process. So the key strength for this tool is that AES GCM guarantees data hasn't been altered or forged, unlike other basic encryption modes, where it generates a unique tag which ensures the data is not being tampered during transfer. Then it supports all key sizes, which is like we have seen previously 128, 192, and 256, where AES 256 offers the maximum resistance to brute force attacks. Then, third is this tool is widely trusted and standardized, where it has also used in TLS, IPsec, and other critical protocols. Another key point is that this tool is quantum resistant, especially for AES 256, where NIST considers AES 256 strong enough for future quantum threats, while offering effectively 1 to 8 bits of security is well above recommended thresholds. Then the limitation for this process or this demonstration, it is for both encryption and decryption processes, it relies on a shared password between the sender and receiver. So if the password is leaked or well made known to other unauthorized users, then the encryption process will be demolished. Then another limitation is that anyone can send an encrypted file to you, but you don't know who is the sender based on although the hash file you have verified using the PowerShell terminal, the algorithm SHA-256, it doesn't really mean that person or the sender is the person you think he is. So the tool doesn't verify the sender's identity. Another key weakness is that nonce or initialization vector is reused, and it is quite critical. Reusing the same key and initialization vector or nonce with this tool is quite havoc. It could potentially leak information and compromise its security, which is the primary implementation failure. So the improvements that we can make for this tool is that, of course, use stronger password instead of having it as plain and simple like my password, like the one I've used in the demonstration. Where stronger passwords are recommended. We can also add digital signatures to verify the sender's identity upon encryption and decryption processes that could help in authenticating the transfer. Then to mitigate or to improve the initialization vector, we can use a 96-bit or a 12-byte random initialization vector value for optimal performance and security.